This video will be a solution to the following IMO problem, which asks to determine all functions f from z to z such that for all a, b, and z, f of 2a plus 2f of b is equal to f of a plus b. So the first thing to notice is that the right-hand side does not change when I reorder a and b. However, you can interpret this reordering as actually relabeling a and b, and in that case, the left-hand side would actually become this. So while these two left-hand sides are not kind of manifestly equal, the right-hand sides are, and this gives us a constraint on f, namely f of 2a plus 2f of b is equal to f of 2b plus 2f of a. And now, grouping the terms involving a and b respectively to their own sides, we see that f of 2a minus 2f of a is equal to f of 2b minus 2f of b. So what this tells you is that the quantity f of 2a minus 2f of a is constant, since this is true for all a and b. So f of 2a minus 2f of a is constant. Say k. And just for example, we could just set a equal to 0 to see that k is equal to f of 0 minus 2f of 0, or negative f of 0. All right. So let's go back to our original expression here. Not sure what happened there. Let's go back to our original expression. F of 2a plus 2f of b equals f of a plus b. Now we can introduce k by doing the following: subtracting 2f of a, but at the cost of adding it back. Plus 2f of b equals this. And this, of course, is just k. Right. And now let's do something to get rid of this f composed with itself. So let's just set a equal to 0 and then leave b alone and see what happens. So we see we have k plus 2 f of 0 plus 2 f of b equals f of b. And f of 0 is actually minus k. So this is actually 2f of b minus k. Okay, well, this, this equation is actually true for all b. So it actually gives us a way of converting f of something into an expression just involving one application of f. And since it's true for all b, we could just as well replace b with a plus b. So we get 2f of a plus b minus k equals f of a plus b. Okay, well, this is great. So now if we go back up here, do this equation, we see that k plus 2f of a plus 2f of b is equal to 2f of a plus b minus k. And now simplifying, we actually see that this is true. And now we do the following trick. So replace f with g defined to be f plus k. And how do I do that? Well, if we add a k to both sides, we see that we get f of a plus k plus f of b plus k, and that's equal to f of a plus b plus k. And with this definition of g here, I can write this in this form. Well, f is a function from z to z, and therefore so is g. It's just a translation, or just a shift by k. So it's actually possible to show by induction that g of n is equal to some constant times n for some a. And now unraveling the definition, we see that f of n plus k is equal to a times n, or f of n equals an minus k. All right, so we've actually shown that f has to be affine linear. The only thing remaining to do is to show what constraints are on these constants, if any. So to do that, let's go back to our very original expression here. And let's just see what happens when we evaluate these terms using the explicit formula. So f of 2a is just a times 2a minus k. 2f of b just looks like this. And then f of a plus b, well, that's just a plus b minus k, and then times a minus k. So it's a bit of a mess, but after some rearranging, you can see that we get this. So one of two things has to be true. Either a equals 2, in which case f of n is just 2n minus k, or a times a plus b minus k equals 0. Well, in the second case, this is actually just f of a plus b. And what this says is that f of a plus b is 0 for all a and b. So that just implies f is identically 0. And you can actually check that all of these, or each of these possibilities, gives you valid solutions. I should mention this is for any k, or just some fixed k. And we've actually shown that these are the only things that are allowed. So we are done.